breakfast. There we go. Excuse me, sorry. This is my second talk today. I'm suffering from a cold, so I'm just about managing to keep my voice going. So I may need to sip from my water occasionally. Right, let's see if we can get this done. So, briefly about me. I've been working in the IT industry for nearly 2 decades now. I've worked for all sorts of strange and interesting places, including government and retail. I was briefly one of those contractors your mum used to warn you about. These days, I work for Muller, as in Muller Corner, Muller Milk. It's a giant German dairy company. I am still waiting, though, on receipt of my free yogurt that I was promised when I started with the company 4 years ago. It'll happen. I'll get there one day. Right, I am eventually going to show you how we can use machine learning to make Jane Austen happy. But first I want to talk about breakfast cereal. Bear with me, we'll get there, just bear with me. So, I have 2 children, and they like to be fed, often as many times as 3 times a day. And in the mornings, they tend to have as breakfast cereal. These are 3 of their very favorite choices: Weetabix, Cocoa Pops, and Cheerios. Now let's imagine for a moment that I wanted to create a mathematical model of the choices that my children make for their breakfast cereal each morning. Now, to do this, you would literally have to record every single day which breakfast cereal they chose and what sort of a monster would do that. But what we observe here, though, is that my kids are a bit faddy. They have their favorite cereal, they stick with their favorite cereal until that one's rubbish, and then they switch to something else, and then they'll stick to that for a bit. So the simplest possible way of modeling this mathematically would simply to make a probabilistic choice for each day. And that would be 9 times in 30 it was Weetabix, 11 times in 30 it was Cocoa Pops, 10 times in 30 it was Cheerios. Simple. So if we go back then through the month and make a random choice for each day, just like this. Aren't I good at drawing? Then we get first Cocoa Pops, fine. Then some Weetabix, great. Then some Weetabix, then some Cocoa Pops, then some Cheerios, and so on and so forth. That's fine. The proportions are somewhere close to right. But what we notice here is that these children are a bit less faddy. These ones are much more likely to choose one cereal today and have something else entirely the next. And that's fine. And they'll just carry on flipping and flopping between the 3 choices. So, although the proportions are right, overall, over the month, we've lost something. There's a bit of information lost in this statistical model. And that's the tendency to stick with the same thing for a while, to stick in one state. So this talk today is going to be about a system whereby you can capture that information and model it. They're called Markov chains. I'll get to them a little more in a minute. But first off, imagine that the whole system is made up of states. And in my case, the states are breakfast cereals, their choice. Cocoa Pops, Cheerios, and Weetabix. And they aren't simply 3 states. In fact, we imagine it instead as state transitions, as the links between the states. So Cocoa Pops can either remain as it is or switch to Weetabix or Cheerios. Weetabix can remain as it is again or switch to one of the other 2, and the same for Cheerios. There are, in fact, not 3 states, but 9 state transitions. There we go. So let's look at this in terms of what the transitions are. Weetabix became Weetabix again 6 times. Switched to Cocoa Pops once and to Cheerios twice. It is twice as likely, given that they're fed up of Weetabix, to switch to Cheerios. Is that significant? Frankly, I don't know. I am operating on a very limited data set and only imagining that 3 breakfast cereals exist in the world. Other breakfast cereals are in existence, although they really are quite consistent in these 3. But Cocoa Pops, 9 times it's stuck on the same again. So given that they've started Cocoa Pops, they tend to stick with that. They like that. Twice they switched to Weetabix, and no time did they ever switch to Cheerios. Is that significant? I don't know. It might be. It might be. It might not be. This is where you need more data to get a more accurate model. But for the purposes of this system, that's fine. Cheerios, 9 times back to Cheerios, 0 times to Weetabix, once to Cocoa Pops. So we've gotten a little bit of information about not only how likely are they to stick with the same choice again, but also given that they're done with this choice, where should we go next? There we go, same thing expressed as percentages. So this is the gentleman who invented the technique. His name is Andrei Markov. He was a Russian mathematician from the 1800s. I imagine there's an awful lot of very clever maths papers written on this subject. Spoiler alert, I am not a mathematician. I like maths very much. It was one of my favorite subjects at school. There is a certain level, though, of higher maths which causes even my eyes to glaze over and suspicious fluids to come from my ears. So I am not I am not going to be giving you mathematical definitions, and I'm sorry. I'm an engineer. You're going to be getting an engineer's description, which is more based in how do I use it. So what are the properties of a Markov chain? They are discrete, meaning it is... Ooh, that went loud. Wasn't that loud? They mean it is one or the other. It may not be both. If there is a concept of both, that will have to be a third state of this, that, or both. But all of the states that we see, they are the only ones that can be, and not a mix of the two. It is only the transitions between the states that we're interested in, not the states themselves. And it is all states, as in add up all the probabilities and you'll get one. There are no other states. There's no hidden state out of sight for the purposes of the model. Now, the real world, of course, doesn't always match the model. In my case, there are other serials. It might be, in my case, that there are very rare occasions that they might like some Lucky Charms or something that we buy from the American shop. That's possible. That's possible. But for the purposes of my model, that concept doesn't exist, and there are 3 breakfast cereals, and that is all there are. Okay. So, going back to that, let's try and have another go at generating some random choices of breakfast cereals for the month, given the Markov chain system, which is based on, given I know my current state, I can make a probabilistic choice of which state to transition to next. And then when I'm in a new state again, I have my selection of probabilistic choices. Weetabix, Cheerios, instant switch, that's interesting, but we'll come back to that. Cocoa Pops, Cocoa Pops, Cocoa Pops, Cocoa Pops, Weetabix, and so on. And there we have it. These kids are much more faddy. These virtual children have a favorite and they stick to it. They're probably sticking to it a little longer, in fact, than my real children, but with more information, then you'd start to get a better model emerging from the system. But for 30 days worth of data, that's not a bad effort. And this is what it looks like. So again, sticking all the probabilities, you can see that you can see where the higher numbers are in the different possible state transitions. In every instance, it's far more likely that we're going to bounce again to the same, with the exception of Weetabix, 0.67 compared to the other two, which is 0.9 and 0.82. So if they start on Weetabix, they're much more likely to switch over. I mean, it's sadly probably because that's a much healthier breakfast cereal compared to the other two. That's probably the explanation. So we can use this to get a little bit more statistical information. There's all sorts of ways of using this technique. The first uses matrices. Now, we've probably heard of the matrix. This is nothing like that. So I was disappointed as anything when I went to university and found out that a matrix is, in fact, just a funky name for a table. There's one. It has nothing to do with shooting people while wearing sunglasses. I think the filmmakers just thought that the name sounded cool. It's a bit like the film Source Code. Has anyone seen that? Yeah. Has it got anything to do with source code? No. They just thought it sounded cool. In fact, the computer's called the source code. Really? Really? So we just didn't have two names? I don't know. Fine. This is Hollywood for you. But what is a matrix? It's a two-dimensional array. That's all it is. And there are ways that you can apply formulae to matrices to create new matrices out the other side. So in my case, what I'm going to do is make a matrix which consists of the from down, the going down, and the to going across. That is, which state am I going from and which gate am I going to? And then put all of my numbers into the grid. So A, for example, is Weetabix to Weetabix. G, for example, is Cheerios to Weetabix, and so on and so forth. We also need an initial distribution in order to be able to do things with this. So an initial distribution is, what's the probability on day one? Now, I can't know that. There's no way for me to know that. So in the grand tradition of statisticians, I'll take a guess, which is not unreasonable. So if I want to work out what is the probability of any given breakfast cereal on day 2, then this is the formula. AX, that is, this is the probability of Weetabix, specifically on day 2. So AX is, there, A is the probability of Weetabix to Weetabix given that it's Weetabix, plus the probability of, there we go, Cocoa Pops to Weetabix given Cocoa Pops. And then add that to that, the probability of Cheerios to Weetabix given Cheerios. All 3 of those probabilities will result at the end in Weetabix. I simply add them all up. That is the probability on day 2 of Weetabix. Right, let's have a look. And then same basic principle for the other 2. You get the idea. Slipping off a little bit, there we go. Right, let's assume an initial distribution 0.3 across the board. It's not really 0.3. Don't worry, I didn't really put that in. It's 0.3 recurring. And then stick all the numbers in, and that means that given that initial distribution, then on day 2, Weetabix is a probability of 28%, Cocoa Pops is a probability of 34%, and Cheerios 37%. Significantly higher probability of those second 2, much smaller chance of Weetabix. And then we could go to day 3. 24.9% probability Weetabix, 34% chance Cocoa Pops, 39% chance Cheerios, and so on and so forth. This is what happens if you stick that process into Excel and run it day after day after day. Now, there's something interesting happening here. If you look, just about here-ish. It's a bit hard exactly to point. But what you see is it goes from a probability which is varying wildly and then kind of planes out and just goes flat. This is called the equilibrium point. Or the equilibrium. There we go. And the weird thing is that no matter what initial distribution you start with, if you run the process again and again and again, they'll always not only reach equilibrium, but it's the same equilibrium. In all 3, it's a little small for you to see, but trust me, in all 3 of these, the final state is always the same thing. So what that means is that if you get to that equilibrium point, that represents the probability on day X of any one of that choice being made. So I now have statistical information that on any random day of the year, what's the chances that my girls wanted to eat Weetabix? Now, if I had better data and if I really were taking this seriously, which I am not, then I might use that to make choices on how many times I buy a new packet of Weetabix versus a packet of Cheerios from the shop. That's information I can use to forecast what purchases I might make from the shops. That's potentially useful. Now, the costs involved are so low that it's frankly not worth the effort in this case, but imagine that you're scaling this up into some sort of business which has thousands of whatever currency riding on it. It also has nothing to do with this film. This film is not a very good film. If you have seen it, it is terrible. It's about 2 hours of people going click, click, click with guns, and Christian Bale looking moody. Watch Batman. Batman is a better moody Christian Bale film. Also, Sean Bean dies in it. Spoiler. But then you probably could have guessed that. He always dies. My favorite Sean Bean film in some ways is a terrible film called Mummies, where he plays an ancient Egyptian mummy who is already dead at the beginning.
So, if I may, I'm sorry to interrupt. One film where he doesn't die?
A film where he doesn't die?
Silent Hill.
Silent Hill. He doesn't die in Silent Hill. Spoilers, folks. But there we go. He doesn't die in Silent Hill. Now I shall watch that and admire him living at the end. He also doesn't die in the Shark TV series. But right, there's my final probabilities, in case you're interested. On any given random day of the year, there is a 19% chance of Weetabix, 36% chance of Cocoa Pops, and a 44% chance of Cheerios, roughly speaking. Let's see what else we can do with this. So that's statistical information. What about strategic information? Who has not played the game Monopoly? Anyone played Monopoly? Yeah, it's not a very good game. It's great if you don't like your family and you want to start an argument on Christmas Day and sort of set the timer before someone flips the board. I would rather play Settlers of Catan myself. Settlers of Catan is a very good game, but much harder to model using this technique, so I am sticking with Monopoly. So, what do I need in order to model Monopoly? Well, I'm going to treat each square as a state. Okay, there are all the squares around the outside, which we can travel to. Jail is 2 squares. Jail and just visiting, it must therefore be 2 states. But that's about it. So those are my states. But I also need to model the changes between them. How's the chances, given, say, go, of which square you'll end up on next? Well, first thing to do, roll the dice. There are 2 dice in this game. They are 2d6, as they say, 2 6-sided dice. The minimum value they can have is 2. The maximum value they can have is 12. But it is not as simple as that, because the probability is not even of each of those values. Anyone who's played Settlers of Catan knows this. Those are most of the combinations. There is only one combination that will get you 2, a 1 and a 1. There is therefore a very low chance of getting a 2. On the other hand, there are 6 ways of making 7 that will get you the robber in Settlers of Catan. And that means that there is a fairly high chance of getting a 7, with the probabilities petering off each side of the 7 peak. There we go, that's expressed as probabilities. There is a 1 in 36 chance of a 2, and same of a 12, peaking around the 7 with a 1 in 6 chance of a 7. Here's what this looks like roughly. So this means we've got a 0.02 chance of the community chest over here. The best chance that we've got of landing anywhere is the chance over here, 0.17, and petering out to 0.02 over here with the electric company. Now, this is a UK board, so I may use different street names to the version that you know, but I shall try and refer to the colours as well, in case you are really interested in how to win at Monopoly. But that's not the whole story, because there is more to it than that. You can roll doubles, and 3 doubles will result in going to jail. So actually I have to triple my states, because I also have to map that. Plus, in the chances and community chest cards, there is a small chance that you will move to another square. This might be jail, Trafalgar Square, back to go again, do not collect £200 or whatever, and so on and so forth. There's various cards that will move you around the board. All of this has to be taken into account, which I have done. You are welcome. You now have a 0.01% chance, that is a 1% chance of being on Mayfair or Trafalgar Square or the community chest still. You have in fact, you have a 1.2% chance of being in jail already. Naughty, naughty you. And we're still the highest probability chance of being on this chance square right here, with 16%. Great. So let's apply this to the whole board, which will take a while. I'm not going to give you the whole working, but if you'd like the results, here you go. So, having done the whole board, gathered all the probabilities, stick in the initial distribution, in which is actually 100% chance of being on go and naught of everything else, and then done it time after time after time until we reach equilibrium, this is what we get. You have a 6.3% chance of being in jail. That is the most likely place I shall find you. Nice. There is a 3.1% chance of being on Trafalgar Square, the most expensive of the reds, or Vine Street, the main orange. There is a 2.85% chance of being on either of the other oranges, another one of the reds, one of the 2 stations, back at go, free parking, and so on. The theme I notice emerging here, if I were making strategic choices in Monopoly about which properties to invest in, I would say green and red are really good choices, because they have, by quite some way actually, because this graph goes on further, the probabilities drop quite sharply after this one. There is a very good chance that on any arbitrary turn, someone's going to be on a green, as on an orange or a red. So I would invest heavily in orange and red. There you go. Now you have your information. Also, the railway stations are pretty good too. There's 3 of them out of the 4. And since they get more expensive, the more you have, those are pretty good choices too. There, you're welcome. How about snakes and ladders? This can provide a slightly different form of information. There's another form of Markov chain, an absorbing Markov chain. This is where there is one state which captures the other states, and once something falls into that state, it cannot escape again, like a black hole. Although we call this particular black hole square 100. So once you've reached square 100, depending on the rules you play, then you generally don't leave it again. For the purposes of my demonstration, you don't. I know there's some where you bounce out again. So what it means is I can get some interesting statistical information about this ancient Indian game. And it is Indian, incidentally. Come on. Come on. There we go. And in fact, this time I did it in Excel. Yeah. Because weirdly, this is easier in Excel than anything else. There is an Excel formula called mmult, matrix multiplication. You can literally make your matrix, feed the coordinates of the initial distribution matrix and the line that you're interested in, and then just apply it again and again and again and again. And this initial distribution set, well, the modeling set this time was given the square and 1d6. What is the square I shall go to? Which mostly would have been the next adjacent 6 squares, excepting that one of them is a snake or a ladder, which I represent then by the probability shifting from whatever that square was to somewhere else on the board. And then that gives me a gigantic 100 by 100 Markov chain matrix with a 100 by 1 initial distribution. And it's pretty big, but there you go. This is what you get. This is the half-life of a snakes and ladders game. Wow. The quickest win possible. Now, bearing in mind, I didn't count. I just gave it all the transitions. The quickest win possible is 11 turns. I don't even know what the combination is. It doesn't really matter. But I know that because only at turn 11 in here does the probability of winning here defined as am I on square 100. So this is the probability on any given turn of being on square 100. As the turns go on. So this is turn 1, this is turn 421. So the probability shifts from no impossible to possible on turn 11. There is a 25% chance of winning turn 38, a 50% chance of winning turn 65, 75% chance of winning on turn 111, and it's not actually a 100% chance, but as of turn 373, the probability of winning is so close to a 100 that it's basically 100. Of course, you can always carry on going in loops and loops forever and ever, but honestly, by 373 turns, I'm probably bored of this game by now. I'd probably have gone to pick up Settlers of Catan, because that is a better game. But still, that is some interesting information you can get, though, about the process of decay in your system. So let's turn now to Jane Austen. If anyone has heard of her, she is one of the greatest writers in the English language, and she's awesome. There are 2 kinds of people in this world, those who think that Jane Austen is awesome and those who are wrong. So this is, in fact, the only... Go away, you. This is the only image of Jane ever drawn from life. There are other pictures. Most of them are redrawings of this one. This was drawn by her sister, who, being charitable, perhaps wasn't the most professional of artists. Jane here looks like she's possibly sucking on a particularly sour lemon. Or could it be because she didn't write anywhere near enough books? Because Jane Austen wrote 6 books in her life. I know there's only 5 pictures. The final 2 were released in a single volume. The most famous, of course, being Pride and Prejudice. This one, at least, is worth everyone reading. It's very good. If anyone has seen Bridget Jones's Diary, you've basically seen the plot of Pride and Prejudice. It's the same story. The same actor, in fact, as one of the other versions. Colin Firth, he gets everywhere. So what can we do? Well, what we do is we treat words as a state. Each word. So the opening of Pride and Prejudice, rather famously, it is a truth universally acknowledged that a man in possession of a great fortune must be in want of a wife. So first, we'll take the word it. It occurs 235 times in the book. 82 times it is followed by the word was, 72 times by the word is, and 11 times by the word would, and so on and so forth, until we go down to single instance of follow continuations from it. Was occurs 1,843 times, each one unique. And so on and so forth. Now, doing that, we can get a gigantic great Markov chain set, and we can start making random choices. I started on an arbitrary word and just let it run for about 500 paragraphs until I started getting something approximating a nice random set of data of text. Now, to do this, I also treated punctuation marks as words, and new lines as words, and chapter endings as words. When I was pre-processing it, I substituted those things for special characters, which then I understood programmatically when I got the data out the other side, so I could re-render it in something like its original form. Now, there are a few issues, though, with this version. A little hard to see with the small text, but we have strange endings of lines where you are so teasing than mine, and if he, where we might have mentioned Mr. That doesn't make any sense. That's not good. The reason is because those things contain full stops. Mr. dot is an abbreviation of Mr. M-I-S-T-E-R. The full stop it cannot distinguish from the ending of a sentence, and so it's getting confused and ending paragraphs in strange places. So fine, there is a way of improving it, and that is to use pairs of words as a state, and then you get a much better result. So this is the process by which I did it. First off, I went to Project Gutenberg, which is the repository of pretty much all public domain texts. In fact, I chose Pride and Prejudice not only because it is a very good book, which it is, but also because it is the most popular text on the whole of Project Gutenberg. Clearly, Jane is still popular to this day. And it's from there that I got the complete text of the book, which looks like this, and then I pre-processed it with a few steps. First, replace all punctuation marks with a space either side. This makes it easier for me to identify them as words. And then I split by new line to kind of get the data into a list of sentences. Stick BR tags. So I use HTML BR tags to represent the ending of sentences, because once this goes through the statistical meat grinder, it's going to be very hard to retrieve where the endings of lines were originally. Select out many, so that basically, select many with a split by space. So what I've done is taken all these sentences with BR on the end, split by space, and then selected many, meaning that all of these little arrays collapse into one gigantic array. Each one is a word, and they're all in the correct consecutive order that they were in the original book. So what you get is, it is a truth universally acknowledged, comma, that a, and so on and so forth. The whole book. Then stick things into dictionaries as two-word chains. So take the first two words, it is. Then look for every instance of that exact two-word phrase, it is, and then look for the next word. So 13 times it is was followed by the word a, 3 times by the word very, and so on and so forth. Is a, 8 times followed by most, 9 times by very. So we're already getting interesting statistical information about the word usage that Jane Austen tended to use. And then I converted it into a structure like this. It is, and then I used enumerable.repeat to literally repeat each word the number of times statistically it was used in the book after that, which makes it very easy for me to just roll a random die, as it were, and then pick one item out of here. If anyone knows a better way, then let me know, because that was the best I could come up with. And then literally loop around again and again and again. I use BR count as my limiting factor, BR being the end of a paragraph. So what I say is, give me 500 paragraphs. That was an arbitrary number, but it gets me some results. And then I got a selection of the first 2 words of each chapter, and then use those as my initial distribution point, and then started making probabilistic choices, and every time moved the pointer on one word so that whatever the second word of my last chain was is now added another word onto, and then we take another choice, and so on. And here it is. Let's see how we get on. Miss Bennet did soon lead to make Elizabeth hope, therefore she was persuaded, lasted no longer than could be overcome at the request of Mr. Darcy. It was only confused for the situation temper. But you see that your resentment does not authorize me to say to her, and whose steady sense and goodwill for being next in the dining room at night, and during part of the party broke up, was a solicitude on the part of continuing her walk alone, crossing the road, reaching Netherfield soon after breakfast. The gentleman experienced some change of sentiment. If it be possible that he has done something towards clearing him, I feel myself called upon by seeing him at last. I know, my dear, you had gone with us to the house. Now it kind of, well, thank you. So that sounds vaguely like Jane Austen, but if you listen to it, I keep getting the sense of like, no, wait. No, I wasn't paying attention. Sorry, do that again. It doesn't make any sense. It's a load of old tosh. But it's a load of old tosh that has preserved statistically the word usage that Jane Austen had. And so a flavour of her voice has been preserved, even though what we get is basically take the words of Pride and Prejudice, run them through a meat grinder, and then pour out this sort of vaguely Austen-y tasting paste. Yummy. So, what else can we do? So, I have to stop us all at this point to issue a trigger warning. You see, some many years ago, Donald Trump stopped using Twitter. And I thought, you know what? I could fix this. So I found a GitHub repository with every single tweet by Donald Trump that had ever been made and ran it through the same algorithm. There is no saving you. Great news, and failing New York Times writes total fiction. The new Congress, but we are in total command and control of massive amounts of snow. This actually sounds like the sort of thing he would have said. Stock market hit another record high. Don't forget Wisconsin. No action or results. We are already very angry. Time to get rich. I have no idea what any of that could possibly mean, but it is very entertaining, unlike the real man himself. So that was fun. So what's the point of any of this? What is the deal with doing any of this rubbish? Well, there's a few uses that you can actually put Markov chains to. Okay, you can use it for statistical information about making choices. I already showed you how you can use it to make some of the best choices in Monopoly. And you could apply this same process to almost any game. Now, the more complex the game, the more exponentially complex the set of Markov links is necessarily going to be. And it's assuming there's a great deal of probabilistic movement going on as well. You could actually use this for things like training it to beat someone at scissor, paper, stone, or however you might call it. You know that game? I know it by a few names. I think the Japanese call it janken. And what do you call it in the US? Rock, paper, scissors. Rock, paper, scissors. Now, you could potentially use it if you watch the same person again and again and again for what they tended to do, and then maybe use it to have a chance of predicting their next move. So you could do things like that. And probably almost any other game, but as I say, these things get complicated fast. Financial information. This is actually used in the financial industry for predicting the behaviors of stock markets, for making financial choices. Effectively, you're trying to predict what's going to happen. This is the Google PageRank algorithm, and that's based around Markov chains. This page being linked from these pages, and then it uses some sort of magic that I don't understand to produce a ranked list based on probability of which page you should be linked to. It's used for predictive text messaging. I hope something nice is going to be written next. But your phone is effectively generating something like a Markov chain model of whatever you write, and then using it to predict, given these words, what are you likely to write next? Your phone is learning you as you use it. Hopefully not in a scary way. Better, thank you. Testing. So you can actually use this. If you wanted to test a system which is constantly producing data, maybe something you're monitoring or logging a behavior or something, you could use Markov chains to gather data about how the system works in the real world and then create a live-like statistical replica of it. You could produce live-like test data, and as much of it as you like. You could have it happening in real time, and it would behave something like the real system. Good enough perhaps for test purposes, but without actually having to maybe implement some sort of complicated software system or stand up an actual hardware device that would need something difficult to be done to let it work. This will work in complete isolation and runs purely off statistics. And then finally, you can use it to make Jane Austen happy actually appears to be in this slightly redrawn version of the original image by her sister, because now she can have just however many however many books you wanted to write as possible, provided you're not expecting them to have any plot. There is a limitation I haven't mentioned of this system, which is that it is only aware of what's happening now and what's happening next. So this is why the Jane Austen is a whole load of tosh. The reason is that it's only aware of this word, and the next word. Once we've moved on a few steps, it's forgotten what it was doing. So it has no memory. There is an overarching structure, which is, in the book sense, plot, character. With my Twitter, there were examples where it bust over the Twitter word limit, and that's because it doesn't know anything about that underarching bit of structure. Of course, the Twitter having such a strong tendency to finish soon means that my random tweets will always tend to be quite short, because it's easy to reach an end state. But still, it doesn't understand that there is a rule. So it has its limitations. So there we go. Are there any questions at this point? Ooh, thank you. Thank you. That's it. Oh, and also I have a book out. Please feel free to buy this book. But
any questions? No? Very clear presentation.
Oh, sorry.
Is the model quite fast, like if you were building a library for word prediction?
Yeah, it's really fast. Like, basically just sort of, like with my Pride and Prejudice ones, even though that's a super large, complicated model, it produces text like that. It's really fast.
So it just looks at the last word. Would it be possible to look at the previous word to make sense, say 3 previous words?
You could, yes. So can you move 3? Yes, you can make the chains as many words as you like. I did it with 3-word chains, 4-word chains, 5-word chains. This is where you get more into the art rather than the science, because the more words you use in a chain, the bigger your chances that it's just going to replicate the actual book. Because eventually you've made word chains long enough that there are no other places that this chain of words exists. So I went with 2 as a slightly arbitrary choice, because it had no real obvious mistakes in terms of English syntax, but didn't feel too much like what had already existed. Although it's hard for me to predict where exactly each of the words in my random generated paragraph came from. They could have come from almost anywhere over the book. As I say, it's gone through the meat grinder in a way. So does that answer your question, sir?
Yes.